Hi guys, today we're going to look at another problem which is about the pendulum with moving support. So let's dive right into it. So basically what we've got is we have a support and we've got a sliding mass which we call M1 connected to a rod through a rod to another mass M2, and so this is basically a pendulum with moving support. So this M1 can slide along this line, and we say that this y coordinate y1 is equals to capital H, and then the x position we just call x1, and this angle we're going to call theta. And what we want to do is we want to find the equation of motion for this sliding pendulum. So the way to go about it is to recap what the Lagrangian is. So the Lagrangian is the kinetic energy minus the potential energy. So the kinetic energy in this case is you have two different kinetic energies. One is for the mass m1 and one is for the mass m2. And for the potential energy, you have the potential energy of the mass m1 and the potential energy of the mass m2. But for mass m1, the potential energy is constant, so we need not consider it, right? Because it's the constant height h, we need not consider it. So let us first calculate the potential energy of the first particle. So the potential energy of the first particle, well, actually, let us first look at the position of the first particle and the second particle. So the position of the first particle, let's call it R1, is just x1 and a constant height h. Now for the second particle, the position is just x plus, and we say that this rod has length L, plus L sine theta, right? Because the distance, let's say this is the origin of the origin, then this distance here is x and this distance here is L sine theta, because this is the opposite side of the triangle for the angle theta, right? So so the position of this particle is just this distance plus this distance, so that's x plus L sine theta. And the height of this particle is just the height of the whole support, which is capital H, minus this distance, which is L cos theta. So we have capital H minus L cosine theta, right? So now to calculate the kinetic energy, all we have to do is we have to first find the velocities of each of these particles. So let us calculate R1 dot. Well, that's just going to be x dot for the x component, and the derivative of h with respect to time is 0 because it's a constant, so that's 0. Similarly, the time derivative of the second particle, of the position of the second particle, is just going to be x dot plus L, and then sine theta, we use the chain rule, cosine theta times theta dot. That's the x component of the velocity of the second particle, and the y component is just, well, you have h, which is a constant, so that doesn't depend on time. L doesn't depend on time. Only the cosine theta depends on time. So you get minus L, and then the derivative of cosine is minus sine, so this becomes a plus. So we can remove the plus sign over here, plus L, and then the cos theta becomes a sine theta times theta dot. And that's it. We now have the velocities of the two masses. Now to calculate the kinetic energy, we just have one half m1 r1 dot squared plus 1/2 m2 r2 dot squared, right? So let us calculate this actually. So we have got 1/2 m1, and then we take the x component squared plus the y component squared. X component squared plus y component squared. The y component squared is a 0. So that's just going to be x, this should be x1. x1 dot squared plus 1/2 m2 And now what we need to do is we need to square the x component and the y component. So we have got x dot plus L cosine theta, theta dot squared plus L sine theta, theta dot squared. Now what we're going to do is we're just going to simplify this a little bit. So we get 1/2 m1 x1 dot squared plus 1/2 m2, and then we get x dot squared plus L squared cosine squared theta, theta dot squared plus L cosine theta x dot theta dot 2 times, in fact, right? So all we did here is we used the binomial theorem and we expanded this term here in terms of with the square over here, and then we have plus L squared sine squared theta, theta dot squared. That's it. Now what we can do is we can simplify this a little bit. So we notice we have x1 over here and x, this should be a 1. This should be x1. x1 we have m1 plus m2 1/2 x1 dot squared. So we took this term into account, we took this term into account, and then we have plus 1/2 m2, and now we notice that this term and this term have L squared theta dot squared in common, and you have theta squared sine squared theta plus cos squared theta, which is equals to 1. So you have m2 times L squared theta dot squared plus 2L cosine theta x dot theta dot. So this is the kinetic energy. That's it. This is the kinetic energy. And now what we need to calculate is the potential energy. So this is the kinetic energy T. The potential energy, well, it just depends upon the height of this second mass, right? Which is h minus L cos theta, right? So we have got that the potential energy is m2 times g times h minus L cosine theta. That's it. That's the height of the second particle. That's the potential energy of the second particle, because we are just in the gravitational field of the Earth, and we consider very small L. So the gravitational acceleration is going to be constant. That's why we've got this g here. You can take a look at my other video about the particle in a gravitational field near the Earth. So this is m2 times g times capital H minus m2 times g times L times cosine theta, and this should be plus because we have, no, you're right, it's right, it's a minus. This is minus, correct, minus. This is the potential energy. And now what we can do is we can calculate the Euler-Lagrange equations, right? So we have d by dt partial L with respect to partial x1 dot is equals to partial L by partial x. And then we have the second Euler-Lagrange equation, which is d by dt partial L partial theta dot is partial L by partial theta. Let us calculate this guy here over first. x1 dot. Where do we get the x1 dot? The x1 dot, we only have one term over here, which is this one, right? So let us calculate d by dt partial L partial x1 dot is d by dt, and then we have got partial x1 dot of half m1 plus m2 x1 dot squared, 1/2 m1 plus m2 x1 dot squared, and this is just equals to, well, you've got the x1 dot squared over here, so that the 2 comes down and we have the linear x1s left. So we are left with m1 plus m2 times x1 dot, and this, according to the Euler-Lagrange equations, is equals to partial L by partial x1. Now the Lagrangian, neither the kinetic energy, as you can see here, nor the potential energy depends upon x1. So this is just going to be equals to 0, and this should be d by dt, like so, right? So we have d by dt m1 plus m2 times x1 dot is equals to 0. In other words, m1 plus m2 times x1 double dot is equals to 0, right? Now that's the first Euler-Lagrange equation. The second Euler-Lagrange equation is basically, let us copy this from here, and we insert it over here, right? So let us call this equation 1, and then we have, so let us calculate d by dt partial L by partial theta dot. This is d by dt, and then partial L by partial theta dot. Let's see what depends upon theta dot. The potential energy doesn't depend upon theta dot, but the kinetic energy does, and it's exactly this term over here. Well, let's do it like this. Okay, so let's do this a bit nicer. Let's move this over here, and then we take this and move it like here, right? So we get that this is equals to d by dt, the half we can take out, half, well, we can also take out the m2, so this is equals to 1/2 m2 d by dt, and then we get m2 L squared. Well, I forgot, this should actually be, sorry, this is equals to d by dt partial by partial theta dot, and then all of this, right? So the only theta dots are in this term over here, and this term over here, and this term over here. So with respect to theta dot, I get m2 L squared, m2 L squared, 2 theta dot, and then I get plus 2L cosine theta x dot, right? Let's check again. 1/2 m2 L squared 2 theta dot, and over here I have 2L cos theta x dot. Yes. So now we can take the time derivative. So this is 1/2 m2, L is constant, the 2's cancel, this one, and this one cancel. So it's just m2 L squared theta double dot plus m2 L minus sine theta dot x dot plus m2L cosine theta x double dot. So this is the left hand side of the Euler-Lagrange equation for the first equation, for the second equation, and this is equals to partial L by partial theta, and this is equals to, this is according to the Euler-Lagrange equation. And let's see, where do we have a dependence upon theta? That's basically let's see, the kinetic energy is over here. We have a theta dependence over here and over here. So we get, so let's take this one out. Well, no. Okay, d by d theta is equals to d by d theta, right? And then we take, well, where is it? The kinetic energy. We take the kinetic energy, paste it in here, and then minus the potential energy with respect to theta derivative, and that's just this term over here. Well, you can take away the minus, because minus, this becomes a mgl cosine theta, and that becomes a plus because we took the minus over there, and that's it. So now we differentiate this with respect to theta. So this is equals to this guy, it doesn't depend on theta, and then we have, and then the 2 cancels over here. So we are left with m2 minus m2L sine theta x dot theta dot plus, well, again minus m2G L sine theta. That's it. So our second Euler-Lagrange equation is just the following. We have got this guy and that is equals to all of this. Right? This is the second Euler-Lagrange equation, and we have to take a look at the first Euler-Lagrange equation again, because there was a mistake. I noticed there was a mistake. I said initially over here that in this equation, basically, I said that the Lagrangian does not depend upon x. Let me see one more time. Let me see, this is the kinetic energy. Yes, the x dot dependence is not only in the kinetic energy but also in this term over here, right? So it's not only the x1 dot dependence is not only over here but also in here. So we have to take this equation over here, and add the second x dot dependence derivative with respect to x dot, right? We already differentiated with respect to x dot. So the second dependence comes from, let's see, kinetic energy is over here. So we get 1/2. So we take this term, add it in here, and then these two fall away, x1 dot falls away, and then the 2 cancels, and what we're left with is m2l cosine theta theta dot. Let's write it down, plus m2l cosine theta theta dot, and all of this we can remove, and then we take this guy, put it up here, d by dt, and then the right hand side of the Euler-Lagrange equation was equals to 0 because there is no dependent of the potential of the Lagrangian with respect to x. So this is equals to 0, and now we can calculate the Euler-Lagrange equation. So we have the equation of motion m1 plus m2 x1 double dot, because we differentiate with respect to time over here, plus m2l sine theta theta dot squared, and this should be minus because we get a minus from cosine by differentiating cosine theta, and then we get theta dot squared, and then plus m2l cosine theta theta double dot, and this is equals to 0. So this is the first Euler-Lagrange equation. So as you can see, it becomes we have two equations of motions now, this one and this one, and it looks fairly complicated, and it is complicated, and usually you don't solve these things analytically. You usually use numerical methods. So yeah, that's it. Sorry, this video was a little bit messy, but we finally arrived at the equations of motion, and next we'll take a look at another problem. We'll take a look at the spring pendulum, in fact, which is also a complicated problem. But you can see, if I had to this calculation, I would not be able to do just from Newton's second law, you see. So this is why we actually do Lagrangian mechanics, because when we use Lagrangian mechanics, the calculation of the dynamics becomes much easier. So this is the reason why we use Lagrangian mechanics. Okay, so thank you very much for watching. Sorry the video was a bit messy, but I'll improve over time. And I hope I'll see you in the next video. Please subscribe if you're interested in more of this type of content, and see you. Bye.